Okay. So welcome everyone. I'm Caitlin Fellow, the Association Director of Seneca Pure Waters. Thanks for joining us tonight for the water quality webinar, Ebb and Flow. There are two segments in tonight's webinar. First, Bill Rogie, Habs Director for Seneca Pure Waters, will present on the 2021 Habs season with information on Seneca Lake and the surrounding Finger Lakes. Then Dr. Lewis McCaffrey, adjunct professor at Lemoyne College, will present on his research of mysterious currents in the deep waters of Seneca Lake. Just a few reminders for tonight's webinar. Please remain muted throughout, and please use the chat box to ask questions. We will pause to have a Q&A session after each section of the webinar tonight. And we will be recording the webinar. It'll be available for viewing on our YouTube page in the coming days. So Bill, go ahead and get us started.
Okay, so thanks everyone for joining us. And for those that are going to watch the recording, thanks for watching that too. So tonight, the first segment is going to be about this year, Seneca Lake and harmful algal blooms or cyanobacteria. And we're going to talk about just briefly our program and what the shoreline monitoring part of the program is, and then I'll allude to maybe some other parts of the program. But I want to talk some about cyanobacteria, what they are, and a little bit of an educational aspect to it, because not everybody has seen them. And then talk a little bit about toxins, and then get into just, it doesn't take too long to really talk about the bloom season this year and compare it to last year and some other lakes and things. And then we'll touch on where we think we're headed for the next year. So the program started in 2014, and really by 2019, we were really a mature program, and it's 2019, 2021, it's been pretty similar year to year. 2017 is when we really started to ramp up. We had set zones and quite a few volunteers. The early years were just a couple of people trying to respond to hotline calls, and we really weren't able to get out and expect to find or sample blooms to really get at it. So the last 3 years are really good cohorts to try to compare to each other and see what our experiences are. So in those years, each year we've covered about 80% of the shoreline, 60 miles or so. We do have some gaps. There's areas that are unpopulated or industrial and we don't have access to or are hard to reach just because of the paints. So I consider this pretty good coverage for the lake. I'm satisfied with that year to year. For Seneca Lake, we run a formal program for 10 weeks from early August to mid-October, but our volunteers are trained earlier on, and they're just not required to report that they looked for a bloom and didn't find one each week, but they're out looking, and they're usually in place by June and July, so we know they're out there looking. And our experience has been is that Seneca Lake doesn't experience early bloom before August. So other lakes, Cayuga particularly, sees them routinely late June and during July. For the last 2 years, we've just been confirming blooms by photos rather than taking samples. Because samples take a while to analyze. It really doesn't help our notification mission, which is to get the word out that there's blooms happening on a particular day. And the photos have proven fairly reliable. It's hard when the blooms aren't very dense, but mostly that works pretty well. And then we have a customized app through ArcGIS that we use to get our data. It actually takes the exact location off the photo metadata, and we get some other information that the NIHAB site doesn't get. But then when we see a bloom, then we make sure that it's uploaded to the NIHAB site. But just to give you an idea of the the zones and the coverage. Here's, we do a map in Google Maps each year, and we assign here on the left the individuals and which zones they have. And you can see around Geneva and all through the north end of the lake, the coverage is pretty good. All the green zones are ones that are covered. People are assigned to them. We get down to the southern end of the lake. Still not bad, except we do have some gaps. The red zones are gaps that people aren't able to volunteer anymore. So, but if you look up and down, there's a fair percentage of the shoreline that we're able to look at and review. So we do need more volunteers year to year. People, they move on or they can't do it or situations change. So we can always use more, and we like to have backup. All right, so what about blooms and cyanobacteria and how do HABs fit in? This is one of Lou's slides that is obviously taken from a reference, but this proves pretty close to our experience in Seneca Lake. And these green highlighted areas in August, September, going into October is the peak of the cyanobacteria time frame. So each type of diatoms and algae, green algae, and then the blue-green algae, and then the diatoms again in the fall when the water's colder. The Seneca Lake does follow this pattern reasonably well, as far as I can tell from looking at our data. So also in this earlier area, so the June, July timeframe, we see a lot of macroalgae, particularly Cladophora, proliferating out there. So that's sucking up a lot of nutrients. But then when that starts dying off and decomposing, those nutrients are now available back in the water. And so when the temperatures are the highest, the cyanobacteria seem to do well. Our temperature tends to peak mid-August. And that's usually when we actually see our first blooms, is after mid-August and the peak in water temperature. Okay, so we have a couple of species that are the most dominant when we've been doing our sampling and microscopic research, Microcystis and Delicospermum, and I'll talk a little bit about them on the next slide. This Pseudoanabana is common. We haven't done good studies yet to see whether, you know, each species has a different life cycle timing wise. That might be a good research project for later on. But the Microcystis is what we're particularly interested in because it generally is the most prolific producer of the microcystin, the liver toxin. Not all Microcystis produces it, and Microcystis isn't the only genera that does, but I think we have some species here because we've seen high toxins over the years. And the next bullet is about why I want to do a little bit of this today. Is when I was coming into this year, I was looking at the data last year, and I found that over half of our volunteers, even though they've been on for a year or two, have never actually seen a HAB in the wild. So even though we have HABs here on the lake, and we had a lot in 2019, they tend to be in certain areas, and we'll explore why that is. But a lot of people had never seen one. So the more we can do to try to help people identify it and contrast it with other phenomenon, the better off we're going to be. And so, and the next bullet is about, we get other, there's other types of things in the lake that can look a lot like HABs. This year we had a lot of duckweed that people seem to mistake for it. Some of the big rains flushed it out of some of the streams and slow moving waters into the lake. But pollen, as you, May and June, the tree pollen looks almost exactly the same, and it's just the wrong time of year, and it's not the right stuff. And we'll see a picture here too, where you can actually see the cyanobacteria out there, but technically a bloom is greater than 25 microliters or parts per billion of chlorophyll A in the blue-green area. And it's certainly visible. I've seen it from samples that are down to around 10. So that doesn't mean that there's not toxins there. It doesn't mean anything else. It just means that's the particular criteria for a bloom that New York State has set up. And so you can see it before it technically is a bloom. So here's some pictures microscopically of the Microcystin and Dolophosphorum. You can see that they have very different structures. The microcystin tends to clump in sphere. You know, the colonies tend to be round, whereas the Dolophosphorum is long and stringy at this level. But we do see them both. They're mixed in, they coexist, and there may be multiple species of each type. These are not just one species. They're I think a genera. But it's just, it'd be interesting to do more microscopic, I think. All right. So what I wanted to do is go through some of the photos that we saw this year and just give you an idea of the different patterns that we see. And I think over the years have been somewhat typical. So the one on the left, it may be a little hard to see because there's wispies in there though. And this is fairly typical of early season. So you get these wispies, you can see it in there, and it's not really clear without sampling whether that would really technically hit the 25 microgram per liter limit. It's fairly dispersed, but again, clearly visible, and it might be close. So then on the right is, you can see the kind of paint streaks and oil streaks in amongst a bunch of other material in there. And that's, again, fairly typical of shorelines, particularly if things have been stirred up prior and there's a lot of stuff in the water like we had this year. But not everything is part of the bloom. It's all mixed in. So the one on the left may look really dense at first, but the green splotches that are really heavy are probably duckweed. And so, but you do see the streaks in the other parts mixed in with it. So definitely, you know, some of those are definitely big enough to be called a bloom. But again, it's mixed in with other things. And so you have to be a little bit smart, I guess, to be able to differentiate between the different materials. The one on the right is a somewhat typical thing that you see right at the shoreline, where you'll get some concentration and you get a lot of these dots that are kind of held together. I've looked at it and it seems like there's kind of a mucus actually that helps trap the cyanobacteria in there. And I've also seen silt and sand and other particulates in it. But this is mixed in with other weeds and things. And I think the weeds sometimes help kind of keep the cyanobacteria together. And then the one on the left is October 6th, which was our big day, and we'll talk more about that later. But this is the typical pea soup sort of look. So very, very intense. One of the most intense blooms I've seen here on Seneca Lake, but definitely cyanobacteria. The one on the right is actually an offshore bloom. And this is kind of what you'll see off there. The wind action and wave action makes these streaks, just like sand dunes or other things that the wind tends to work with in particles. This was taken September 30th, right off the yacht club, so at the north end of the lake. But it was out in open water, so they're not all right at the shoreline. All right, so how do blooms actually form? Now, this is the typical way. There's potentially other things that can happen. But typically, the cyanobacteria are dispersed throughout the water column. So the blooms happen when something triggers them to go into metabolic overdrive, and the carbohydrates lead them to become more buoyant, or somehow the buoyancy is activated. And so that whole, who knows, 30 feet of water column that's getting good sunlight and they're going to town, that now concentrates into a floor, a thin layer at the top of the lake. So just like that last picture we had, that's this kind of concentration. And then, so that might be 100 times the normal concentration. And then when you get a wind, particularly a slight wind, that's going to push all those particles at the top of the lake in one direction. So that's going to concentrate them even more. And that could be even more like 1,000 times more concentrated. And then they get pushed along until they get stopped by something or trapped by something. And so that's why we see them at the shorelines mostly, is that they've been pushed in there and concentrated to such a point that you see now the pea soup sort of picture when it gets into a cove and it's trapped and it's calm and it just keeps piling in there. So that's really, so the blooms don't necessarily form right where we actually see them. They're not mobile and they're not moving on their own. They're going by the winds and currents, and they go wherever they are. Okay, so let's talk about toxins a little bit. The microcystins I referenced are the most common that we have, affects the liver, but it's not very stable. Well, no, I can't say that. That's the wrong one. It may be very stable, but that's the most common one that we see. The anatoxins, the nerve toxins, which are particularly with dogs, these may or may not be stable, but part of it is that the toxins are contained inside the cells. So if you get a bunch of the bacteria on you or on the dog's fur and they're licking it and doing stuff, they're definitely going to get intake doing that. The lipopolysaccharides are the skin irritants. Almost all of them do that. So if you're going swimming or put your hands into a bloom, you're going to get a rash. And we've had people, unfortunately, forget their safety protocols and do that when they're taking samples. And then there's other toxins out there, but these are the most important ones. And the key is, though, is that they're all invisible. So you're not going to see them. We don't know yet whether they're present outside of an active bloom area. So far, it looks like it's possible they are, but generally not. But there's still a lot more work to be done on that. And then there's a lot more work to be done as far as understanding toxins, where they are and how they're produced. I wanted to talk a little bit about a field test kit for toxins. It came out a couple of years ago. There are other ones on the market, but this one made some good claims and seems to have some good science behind it. Last year, we started testing it and trying to reference against lab samples, but we didn't have very many tests blooms last year, and then actually not a whole lot this year where we had the test kits available. But it's advertised to get down to 1 part per billion, which is the WHO drinking standard, and that's pretty low. The recreational standard here in New York is 4 parts per billion, which equates to about the 25 micrograms per liter for the bloom. But it is pretty easy to use and relatively cheap at around $35 on Amazon. Just takes about 20 minutes to do. And so we're going to still look at it, but I just want to make people aware, if they'd like to try it, I think it's worthy to try. I can't vouch for, total accuracy, but it seems fairly useful from what our experience has been so far. Okay, so let's talk about our HAB experience. So this is a list of our HABs. The middle column, or the second from the right, is the number of confirmed HABs. 2018 and before, we only reported when we sampled. And in 2018 and 17, we were limited in the number of samples that we could take. So in 2017, we were funded for 60 samples and we took them. And in 2018, we had, I think, funding for enough. It's just we only saw the 41. But you can see on here, generally, particularly of late, most of our samples are high toxins, and high toxins is when you get over 20 micrograms per liter. So that's equates to kind of a moderate risk of problems. Now in 2019, we actually, we took 96 samples, but we only sent 40, which was our allotment, for toxin testing. So that's that last side of the table there. So 34 of the 40 we sent in were high toxins, but there's 56 of the samples that we never sent in for toxin testing. But a number of them were confirmed as HABs with a fluoroscope, and we had 130 total because we started confirming even without a sample. So we started using the photos that year to do that, and that was kind of a proof of concept that we could use that going forward. So in 2020, DEC stopped supporting the sampling. We decided we wouldn't pay for it, partially because of COVID and we didn't know the money situation. But as it turned out, we just didn't see very many HABs last year. It was striking, particularly given the year before when we saw so many. This year, we saw 72, and a HAB is each of the zones seeing a HAB in a particular day. So there might be multiple places in a zone, but we only count once for each zone. All right. Come on, go. All right. So let me just go to the map first. All right. So what this is the yellows are the HABs that we had in August. And you can kind of see that they tended to be on the southern end of the lake and fairly well distributed. In September, they were pretty well distributed all along the lake. We only had a few days where we really saw them, and September 4th and 16th were the biggest days. Other than that, we didn't have a whole lot, but we did see them all around the lake. And then in October, and again, this is mainly October 6th, the whole north end of the lake really lit up, and we had a few sightings in the south end, but it was particularly a northern end thing. All right. So what's interesting to me is I like patterns, and you can see for this year, it skewed a bit more toward October. September and October maybe were fairly similar. August was similar to last year, but last year had almost none in September and October, very little. And then in 2019, though, we hardly had any in August, a ton in September, and then, fairly similar to this year in October. So last year, the best we can think of, and I was watching this year too, and for September, is that we had a lot of winds. This year we had, I counted a week straight, like 6 days straight of south winds of fairly good force, and the waves are just going to chop up and prevent the blooms from happening. And one of my colleagues had said that he had attended a session where typically September is the calmest month of the year. So maybe there's some climate change issues with that also to change that. So here's a graph of along the bottom is the day, And then along the y-axis is the number of confirmed blooms that we had on that day. And then the blue is comparing it to Canandaigua Lake, and the orange is Seneca Lake. Canandaigua actually had a couple of blooms at the end of June and the beginning of July that I cut off just because of the scale here. But from mid-August on, you can see that the patterns are actually fairly similar. There's scattered ones in August. Typically, both lakes have a lot over Labor Day. This year, just Seneca had some on the 4th of September, but not much other than that. And then we spiked on the 16th. Canandaigua spiked a couple days later when we had a few, but then both of us spiked. Canandaigua was a smaller lake, but both of us spiked on October 6th, and then had a few other events happen into October. And Canandaigua or Cayuga spiked then, Keuka spiked then, so everybody spiked on October 6th. So we'll talk about that now. So we had 30 blooms, and as I said, mainly in the north, but it was spread out. It covered the entire lake, so you could, on your boat, you would see it just like that other picture I showed you. It was that way all across the lake. And so it was pretty intense for us over the last couple of years. But the interesting thing was, even though it was dead calm across the region, so that was everywhere, but we had an overcast. So it wasn't a bright sunny day, and the water temperature was already getting pretty low. So it was around 60 or low 60s, which should be starting to shut them down. And so it's just like, since everybody had the blooms, we're not exactly all connected. It's like, how do they all know to do that at the same time? And this is kind of the mystery of cyanobacteria and habs and blooms, is there's something going on, and no matter what sort of things we look at, we can't seem to pick the exact, oh, it's going to bloom today. In fact, John Halfman had already told me that, oh, it's too cold, they're not going to bloom now. He's going to take up all his dock equipment that we use to look for blooms too. All right, so next year, we'll definitely keep going. This has been a great program, a lot of enthusiasm and great volunteers. We do have a program where we started another app where people can report offshore that we've been piloting for the last couple of years. So we'll probably start to expand that, because we do see that there are blooms offshore, and we'd like to know more about that. Sampling is still up in the air. We're trying to figure out what a good, valuable sampling program would be, because it is, it's more complicated to do sampling, and we want to make sure it's worth it. So if we don't do some of those things, it's possible that we decide to look at things like Cladophora. It is being studied heavily on the Great Lakes, and they have the same issues with the mussels, and we certainly hear about it quite a bit on Seneca Lake, and I think there could be some confusion about this big mess on my shoreline, and is that a hab? And it's, no, but it might have cyanobacteria inside of it too. So I just wanted to kind of finish up by reminding everyone that the mussels are there, and they certainly are highly correlated to habs, but the intensity and the frequency is certainly influenced by the amount of nutrients that are in the lake. And nutrients have a lot of different sources, and a lot of us, and individually in our homes, take care of things. If we have businesses, taking care of issues there, but we have point source and non-point source issues. And I think one of the things that we really need to be looking at with climate change is stormwater control. So the ditch systems and catchment systems out there, is how do we control that runoff so we don't get these huge rushes of water that not only bring the nutrients in and the sediments, but destroy property. So it's in everybody's interest to try to work on this together. So with that, as Caitlin said, we'll open it up to questions. Might have gone a couple of minutes over, but certainly if a couple questions, so give it a shot. Caitlin?
Yeah, great. We do have a couple questions in the chat, and if anybody else has questions, please, you can enter them in the chat or you can unmute yourself. But we'll start with just the chat questions that are already here. The first question is just, how are Habs confirmed?
Well, as I mentioned, so there's a couple of different ways. We are doing it just via photos. So, and that's what NIHABS does. So the state does the same thing. The volunteer uploads photos, describes it, and then so you look at it and try to make your best expert guess on whether that's really dense enough to be a HAB and the right phenomenon. The other way is Canandaigua and Cayuga both are still doing sampling. So a volunteer will take a sample bottle and we transport it to generally the Finger Lakes Institute in Geneva, and they have a fluoroscope, which is a machine that can quickly measure the chlorophyll A in a number of different color bands. And so they can tease out the total chlorophyll, the green chlorophyll, which is a regular algae, and then the blue-green, I think it's red and brown. But we're interested in the blue-green particularly. And so they can tell you whether it's greater than 25 micrograms per liter, which then says it's a bloom.
Okay. How do we know what types of toxins are being produced? And this is a question, with the concern that some toxins are more dangerous than others.
Well, unfortunately, it's we're not really testing for all sorts of different kinds of toxins. So after we do the screening for the bloom with the chlorophyll A and the fluoroscope, then not all the samples are sent for toxin testing. So the toxin tests are a separate test. But generally, we are only testing for microcystin. So unless we had a specific research project to look for other toxins, we wouldn't find them.
Okay, and can you comment about testing for the cyanotoxin BMAA?
No, because I don't know. We haven't ever tested for that. I don't know anything about it.
Okay.
Sorry. Ian has his hand up.
Okay, Ian, do you want to go ahead and ask a question?
Yes, thank you. I was curious, and this is a hypothetical question, but Bill, if you had unlimited resources, how would monitoring a lake, like say just Seneca Lake, like how would you go about doing it? Would there be buoys along the stretch of the lake, down the center, or at larger areas where we know runoff is coming from that's rich in nitrogen and phosphorus? Any sort of just basic things like temperature and pH and wind and those kinds of things. Would those be the tools that would be necessary in order to help predict potentially, or is it still there's just something out there that's just unknown to this point?
Okay, so we got another half-hour session here. We actually do a lot of those kind of monitoring. So there's buoys out in the lake gathering stuff. We have our dock monitoring program that takes weather and water temperature types of things. Probably where some research has been going on is trying to understand the distribution of the cyanobacteria in the water column in the non-bloom times. So I think having more kind of full-time probes in there to monitor that in more locations would be helpful. There's a little bit of that, but it's very difficult. The lake being so large is kind of difficult. So it seems like most of the research projects have been in smaller bodies. but there's a lot going on. I would like to know, and this is going to be a segue into Lou's, is, you know, the currents and how all that works. Maybe not just the deep currents, but you know, I watch off of Kashan that I think it has a south current bias. If there's a south wind, it pushes the mud north, but when we have a big rain and there's kind of no wind, it all kind of comes to the south. And then I think that's why I have a real sandy beach. So I think understanding more of the more micro terrain interactions and how the inputs, like you were saying, Catherine Creeks and the big streams and the outlet and some of those major tributaries, how those interact with the lake there and what the currents are and how the nutrients might be distributed in the short term.
Okay, we do have a number of other questions in the chat. I'm going to just answer or read two more aloud, and then maybe Bill, as Lou goes on, you can check into the chat and answer questions as they're coming in related to HABs.
Right.
One of the questions still here is, anyone testing for foam on Seneca Lake?
Well, I'm not sure that testing is the right thing. We have been kind of looking for it, but there's been a couple times where people have said they've seen it out in the middle of the lake, but it's nothing like Canandaigua.
Yeah. Okay, and can you comment on the nitrogen and phosphorus levels in Seneca related to other Finger Lakes?
We're higher than Canandaigua and lower than Cayuga.
For both nitrogen and phosphorus?
I think so.
Okay.
I'll take a look at the chat box and try to answer the other ones.
Okay.
Time for Lou to get on. It's a good segue.
Alrighty.
So without further ado, I know there's a lot of interest here. I'll try to answer them, but Lou McCaffrey is, I think, adjunct professor at Lemoyne, and he conceived a really cool project this summer to try to investigate some of the currents, mysterious currents in Seneca Lake, and he has graciously agreed to give us a pitch on it, and I think you'll find it extremely interesting. So take it away, Lou.
Thanks very much, Bill. Thanks for an interesting talk. Can you stop sharing your screen and I'll share my screen? Okay. Bill, can you see that okay?
Yes.
Okay, great. So thanks everyone for your interest. And so I'm going to talk for perhaps 25 minutes about our project to try and understand the deep currents in Seneca Lake. These are only initial results, and so there's still a lot of work to try and digest exactly what has happened there. Let's see. So I'm going to talk about how we measured the deep currents, or how we attempted to measure them. I'm going to talk about the likely causes of those currents, and that's a phenomenon, spoiler alert, called a Saches. And I'm going to talk about the further work that we're doing. And this little picture of the fisherman and the little dog out on the lake reminds me of why we started this work in the first place. And that was because I'd heard from fishermen that they were experiencing strong currents, deep currents, and that there seemed to be no rhyme or reason to them at times. And in my other job, which is working as a research scientist for DEC, I had been putting down some profiling equipment and found it being pulled in various different directions. I just have to, that reminds me that I'm wearing a completely different hat tonight. Really, this is my Lemoyne hat, and I'm here only as a professor from Lemoyne, not in any other capacity. So how did we actually go about trying to measure the currents? Well, we built some equipment known as drifters, but to give them their full name, they're Lagrangian drifters. But the purpose of them is to kind of anchor themselves in the current at depth using this structure. It's called a drogue, also known as a sea anchor. and it's quite large. It's 4 foot by 4 foot with a weight on the bottom. It has a little temperature sensor on it as well. And that's suspended by a tether from a float. And this is a picture of one of the floats. Inside the float at the top, it has a GPS unit, which transmits to a satellite. And on top, critically, it has a solar-powered beacon. And the point of this is the float is low drag, so it moves through the water very easily. And the point of the drogue is that it's high drag. It's kind of anchored in the water, so it goes wherever the water takes it. And in that way, we can move the float wherever the drogue goes. So I had the assistance of 2 willing students, and this is a picture of them drilling the panels for the drogue. This is what it looks like in the calm of my driveway. And this is what it looks like when you're trying to deploy them on a boat in the middle of a very windy and wavy Seneca Lake. And in fact, it was so bad that we actually had to go back to shore and put it all together and then deploy it. So we had quite a bit of fun doing that. This is the area that I had to tell the Parks Department, Office of Parks and Recreation, where we were going to deploy the drifters. And I chose this area off Long Point, more or less in the middle of the lake. This was the deployment area, and this is the area that I expected them to move to over the period of their deployment. And this was originally going to be 7 days. Just a side note here, I had to get a permit for this, and I applied for a floating object permit, but the powers that be decided that since they weren't anchored, they couldn't give me one of those permits. Instead, they gave me a regatta permit. So I think that this was the smallest and most disorganized regatta that has ever been held on Seneca Lake. This is actually where the drifters went to. You can see that we're looking at a much larger area on Seneca Lake. They went up to 16 miles north to south. And this was much, much further than I expected. And that's still not exact. We haven't done the calculations to show why it was so far. But that was an interesting result in itself. Now this looks like a bit of a mess of spaghetti, so let's break it out into the different drifters. We had 3 different drifters deployed at the same time. The upper drifter was with a drogue at 3 feet. The middle drifter in blue was at 30 feet depth, and the lower drifter at about 100 feet is shown here in green. So even this is a little bit of a difficult thing to see. And in the next slide, I'm going to show you an animation. Just to point out that the surface drifter, when we first deployed it, was blown immediately within 12 hours down to the shoreline where it was collected by Addie Mason. We then redeployed it to the same point where it was promptly drifted further up north and then back down again. The deep drifter, or the lower drifter, repeatedly got stranded on the shoreline on the east side of the lake. And that's the reason why you can see that there's a whole series of clustered locations around here. The great surprise to us was the middle drifter. And let's have a look what it looked like. It did actually go missing. And some of you may have seen this on Facebook. The GPS unit batteries gave out unexpectedly. They were supposed to last for many weeks, but they only lasted for about a week. Happily, the solar-powered light continued to work. And this is a video sent in by Carol Armstrong. You can see about here somewhere, there's the drifter light. So we had 300 shares on the Facebook campaign, And finally, on a dark, calm night, we had Carol actually called in, and the volunteers, Larry and Sue Martin, Dan and Laurie Corbett. Dan and Laurie went out and collected it, but the rest of the people here, Bill himself, Addie Mason, were all very, very important in terms of deploying and retrieving these drifters. We couldn't have done this project without them, so thank you for that. And eventually we did get all of the drifters back. So the drifters in motion, this is an animation that I'll start in a second, but I just want to point out a couple of the features. You'll see that the middle drifter oscillates north and south of Long Point. It certainly has a couple of spectacular eddies, which I'll talk about in a little bit, up to a mile across. The speed of each drifter definitely is different. The surface drifters go very fast. The middle drifters go middle, and the deep drifter really tends to be pretty slow. They get stranded and stuck. I've talked about the red drifter, the surface drifter gets removed and then replaced. You'll see that in the animation. And definitely the GPS signal is intermittent at times. That may be due to wave action, but that's something that we will look into. So I'm going to run the animation. Keep a lookout for all of those features that I mentioned. The maximum velocity of the fastest drifter was 0.6 miles per hour. And that was often as they were passing the headlands. And I suspect that that's because the lake cross-sectional area was smallest in that area. And so water had to speed up. You can see some of the crazy gyrations that these drifters were making over the 10 days of their deployment. And that was one of the most astonishing things for me, that they were so mobile. And you can see at this point, the blue middle drifter disappeared from our charts, and the surface drifter headed off to the south. If you want to have a look at that animation, it's on YouTube, and Caitlin is going to put that in the chat. So all of that is kind of amazing, but let's try and get to some science on this. So breaking down the movement, I isolated just the north-south movement and put it on this graph as north and south. And this is time from this date of deployment until they were recovered. So the middle drifter here is in blue, and you can see that it actually goes up and down, north and south, in a pretty regular fashion. In fact, it's approximately 53 hours between each of these peaks and each of these troughs. And we also were able to eventually recover the middle drifter with its thermal sensor, and we found that the temperature sensor was around 17 degrees centigrade, about 60 degrees Fahrenheit, and it more or less was constant and cooling off slowly. Nothing really remarkable there. The other thing that we found was that these turns were quite sharp. We would expect them to be sinusoidal, more like a wave, but they didn't turn out to be that way. In green, we've got the latitude of the lower drifter, and it was certainly more sluggish, but you can see that we've got some inflection points on its travels that kind of mirror the inflection points of the middle drifter. The black line is the temperature that was experienced by the lower drifter, and you can see that it is much colder. It's around 7 to 8 degrees centigrade. That puts it in the cold lower layer of the lake called the hyperlimnion. Interestingly though, about the time that the middle drifter turns north, we see a little kick in temperature. And this occurs at fairly regular intervals. And we do think that that has got something to do with the change in direction, which I'm going to get onto in the next slides. So now to the likely causes. We think that the deep currents are caused by Saches. And if you haven't come across Saches before, I'm going to explain them. They happen when a strong wind blows across a body of water. The wind transfers its energy to the body of water, the lake, and it pushes the water to one end. And it increases the water elevation at that far end, possibly by only a couple of inches at times. On the Great Lakes, it can be several feet. But when the wind stops blowing, that water then starts to equilibrate by gravity, and it flows back towards the direction that the wind was coming from. And that starts a rocking motion. And this happens on the water surface, but critically, it also happens in deeper layers. If you want to see a video of what happens when a sage occurs in a swimming pool with some kids in it, you can click on this link. Caitlin, I think, is going to show that in the chat. Okay, so at the risk of confusing you, I'm going to talk about surface Saches, and then I'm going to talk about deep Saches or internal Saches. Surface Saches don't, we think, cause major currents, but they're interesting, and we've got great evidence for them. This is Seneca Lake elevation from the NOAA gauge at Geneva. It's relatively coarse resolution, 15 minutes, but you can do some manipulation and come out with a really clear graph of when the water surface is elevated and depressed. Over what frequency range. And we found that the highest peak, or the greatest frequency, is at around 54 minutes. We also, this year, Middlebury College and I put in some high resolution loggers in Watkins Glen, and thanks very much to Jim McGuinness and Tom Manley for that. And you can see here that we've got a very clear up and down variation in water level. It's quite short, it's only 3-4 inches maximum. You wouldn't really notice it. And it's also at around 54 minutes. So we do know that Saches exist on Seneca Lake, and we have been successful in measuring them. What about these internal Saches? These, remember, are going to be variations in the elevation of the boundary between the warm water at the surface of the lake and the deep cold water at the bottom of the lake. Now, these have been measured and looked at for many decades. In fact, a professor from Hobart and William Smith College published on this in 1974. He spotted just a one-sided wave, what he called an undulate surge. And I wonder if this is partly because of the duration of time that he was looking and the instrumentation that was used. With modern instrumentation, we can all get access to this USGS data. A sensor was put in at the north end of the lake, and it detected, I won't go into the details of this, but a fluctuation in temperature, periodic warming at 100 meters depth at about the same time of the year that we are looking at in terms of our drifter project. And this is evidence that there is an internal surge. So the interesting thing about Saches is that Saches make currents, because if you're pushing water to one end and it then surges towards the other end, well, clearly water has to move from one end to the other. And you'll notice that this is going to be the area of the fastest current velocity. It's also the location where the surface elevation doesn't change. Eventually, once no further energy is put into this system, those Saches will peter out. They'll eventually disappear due to friction with the sides of the lake. Now, at the risk of putting up some equations, and I've been told that for every equation you lose half of your audience, so that's a half, quarter, approximately 1/8 of you will be remaining at the end of this slide. Not to worry about the details, but the average measured frequency of our internal Sach was about 53 hours. The predicted frequency, given some assumptions and some measurements, was about 56 hours. So that is a pretty good fit with theory. The other interesting thing is that this frequency shows that the phenomenon is probably not linked to Earth-Moon tides, since that is going to have a frequency of around 12 to 24 hours. It doesn't fit in with that 56-hour frequency. So let's have a look at some conceptual models for a north-south Sach on Seneca Lake. Here we've got Geneva, Dresden in the middle, Watkins Glen. And what we see for a start is that we know that Seneca is not an open-ended basin. We've got shorelines at each end. So let's exclude those models. It is a closed basin, and these are to do with the number of nodes that there are in the lake. And we know, for instance, that we've measured very, very low amplitudes, or next to no amplitudes, in Dresden, whereas this one with 2 nodes would have very high amplitudes. So we're going to get rid of that one, and those with 2 and 4 nodes. And what we're left with, beg your pardon, what we're left is a likely 1 or 3 node solution, which means that we're going to have no waves in the center, but higher waves at the north and south ends. Another interesting thing that we spotted were these eddies. Now, this is a picture from space of the area between Japan and Russia. And you can see, because of the lots of suspended sediments in the water, you can see that there are eddies very clearly spotted downwind of these headlands. Now, we think that if perhaps Seneca Lake had more sediment, we might be able to spot these, but it's difficult to see them. And what we have spotted, though, is that we think that these downstream eddies happen about every 27 hours from at least Long Point. I've got a couple of research students, undergraduates, working on this. Jacob Stewart on the left there is working on the wind to make sure that our drifters have not been unduly moved around by the wind. And Berdem Oz is working on measuring and calculating the drag coefficients for the float and the drogue. We have to ensure that there's at least a ratio of 1 to 40 so that the the float is not dragging around the drogue. Further work that we've got planned, I've got a high school student who's going to be putting together a physical model of the lake just for visualization, and it would be really cool to get some good video from that. We're going to search the satellite evidence for eddies, evidence of eddies, just to see if we can visualize it. There's a possibility that we will redeploy in August 2022, and we'd like to try and coordinate that with water level loggers and possibly other current devices. The reason for it being August, it'll be really nice weather, but also the lake conditions should actually increase the frequency of any oscillations quite measurably. And we also want to understand how these Sach generated currents, if that's what they are, how they interact with other currents which may occur in the lake. And there are a variety of other currents that may be possible. So I'd like to thank very heartily the Seneca Lake volunteers who deployed and recovered the drifters, and also those that deployed loggers. I'd like to thank Lemoyne College for giving me a professional development grant, and also Middlebury College and USGS for the data that I've used in this talk. So thanks very much for that. The dog's just about to start barking, so I will mute myself and wait for any questions. Thanks very much.
Wow, thank you, Lou. That's really fascinating stuff. I don't know that any of us have, except maybe one or two people on the webinar tonight, have seen anything or any research been done with the nature of currents on Seneca Lake. So that's really interesting stuff. We do have a couple questions here for you. Let me scroll down here. Have you plotted wind speed or direction versus the drifters at the surface or deep water? Oh, you're still muted.
Yeah, we have yet to do that, but that is actually going to be the task for Jacob Stewart. So we recognize that some people may say, well, this is just being blown around by the winds. A really quick look at the wind data shows that that's not the case, but we want to be absolutely sure about that. So we will be doing it.
Okay, great. Let's see. Do we have any info on the super deep water of Seneca Lake and how that interacts with the upper level of the lake?
We only got to about 100 feet. So the brief answer is no. The super deep water, I would expect to be almost stationary. But there's a possibility that we could always deploy a fourth drifter with a drogue at, I don't know, 300 or 400 feet and see if that did anything.
Okay. Interesting data. Is there any broader, what is the broader scientific significance?
That's a great question. The broader significance is, I mean, it can be applied to a whole series of different problems. One that Bill previously talked about is the effect of currents on harmful algal bloom dispersion. We're also interested in making sure that this data, or at least these concepts, are available to hydrodynamic models of the lake, which might be put together to try and model dispersion of pollutants of various kinds, sediment, water. I won't go into which kinds of water, but there's a whole series of applications for this. And one of the things that we spotted was the bathymetry that we have of the lake is inaccurate enough that our 100-foot drifter was crossing areas that had been mapped at 13 feet depth. So clearly we need to get better bathymetry control.
Okay. I think a follow-up to a question earlier, have you looked at wind speed, direction in relationship to the Psyche frequency? I apologize if I'm mispronouncing.
Yeah, that's the project that Jacob Stewart is going to be working on.
Okay. And will the links be shared by email that I've shared in the chat? As long as Lou and Bill are okay with that, I'd be happy to share those.
That's absolutely fine with me.
Okay. Any other questions? You can unmute yourself. We do have a couple more minutes, and I know that Bill was planning on answering a couple questions in the chat.
I would like to just, here on the right of the slide, as part of our testing process for the prototypes, we went out on Skinny Lake, and unfortunately we lost one of our early prototypes. We'd love to get it back. It's in this particular area on Skinny Lake, so if anybody is watching or watching the video and you come across this, please get in contact.
You can share your email through the follow-up email as well. So if that is it, I will share those links and, follow-up information after the webinar in the coming days. Lou, thank you so much. Bill, thank you very much. Two very diverse sets of information here displayed tonight. And, it's really important to us to share and educate our members on research going on in Seneca. We really appreciate your time. So thank you, everybody. Have a good and healthy, happy holiday season.
Thanks, Caitlin.
Everyone.
Well done setting it up. Appreciate it.
Sure. Take care.
Thanks. Had a great
Take
time.
care, everybody.
Thank you. Bye.